Hello and welcome to lecture number 18 of the course Robot Motion Planning. In the last class we looked at motion planning in systems which are subjected to kinematic constraints, that is non-holonomic constraints, like a car which cannot move sideways because there is a velocity constraint. Now we also looked at the concept of controllability, and we saw that although the car is subjected to a single non-holonomic constraint and it cannot move sideways, but even then it is fully controllable. That means it can go and park at any position in the workspace. Now today let's complete the discussion on controllability and then move on to the next topic, which is the multi-fingered robot hands. Okay, multi-fingered robot hands which are used for manipulating objects. For example, you have a multi-fingered hand like this which has maybe 3 fingers. Okay, a robot hand with 3 fingers, and when you catch an object and you manipulate this object, say something like this, I'm holding this mouse and I'm manipulating it. First is I'm grasping the mouse. For example, I'm just grasping it like that. That is grasp. Okay. Second is after grasping, I am manipulating the object. I'm moving it in some direction like this. Now this fingertip point and this object is also subjected to kinematic constraints. Okay. That means it can move freely in some direction. It may not be able to move freely in another direction. That is something we'll look at today after we complete our discussion on controllability. So in the last class we were talking about motion with kinematic constraints. For example, we talked about this single wheel, which can rotate about an axis. So it can rotate about that. That means it can roll forward or backward, and it can turn about this axis. So this is my steering. Okay, this is very similar to this particular case where, which is a unicycle. For example, this boy who is riding the unicycle, when he paddles, this moves forward. So this can roll forward in this direction or backward, and it can twist about this axis. Okay, so it can basically roll forward, backward, and twist. Now in such cases, we see that it cannot move sideways. Okay, for example, this wheel that I just drew here, it cannot move sideways because it is subjected to a non-holonomic constraint. So, but if I want to make it move sideways, there are a sum of motions which I can perform by which it can move sideways. Now this wheel can move forward and backward. Okay, it can rotate about its axis. So that's my rotation about the axis, which is the steering actually. So if you see a car which is made up of 4 wheels, each of the front wheel can be thought about like this. Okay, and a unicycle, of course, is the same wheel that is being shown in the video here. Now it cannot go sideways. So I cannot make it go sideways like that because of that single non-holonomic constraint. But if I wanted to go and park it sideways, that means I want to park it or place it at some other configuration in the workspace, then what I can do is I can make a series of maneuvers, or I can perform certain motions and a collection of motions such that which will enable the wheel to go and park sideways. And what are those motions? First, for example, I go straight, then I rotate. Okay, that is my second motion. Third is I go back, and then I rotate again. So by performing these 4 actions, you can see that the car can go and this wheel can go and park itself in any orientation actually. Okay, and this is what we mean by controllability of the problem. Okay, that the system is subjected to a non-holonomic constraint, but it can still go and park at different locations because it is fully controllable. This was the example of the unicycle. Now, if I take the top view of the unicycle, this is my top view and this is my central axis. Okay, suppose I'm seeing from this direction. Okay, and I want to make the unicycle go and park here. Okay, so what I can do is I can take it forward in the front direction. I can move it in the front direction. That is, it rolls forward and goes here, comes to that location. That's my axis. Then what I can do is I can use a steering angle, and it turns like this. Okay, that's my steering angle like this. And then it comes backward like this till here. Okay, so now it has come backward like this and it is positioned like this. Okay, then what I do is it has come backward and is positioned like that. And then what I do is my fourth maneuver is like this. I turn it on that side. So if this is my theta, then that's my minus theta. Okay, then I turn it this way, and this comes and parks here. So which means that I can park it anywhere. I can park it here, I can park it here, I can park it here, I can park it here. Now I may be able to park it with just these 4 maneuvers. Suppose it's very far, I'm here, and I want to park it here now. Okay, so I may not be able to park it in just one maneuver, but I can do a series of maneuvers like this. Okay, and then go and park it there. Okay, so this is a path planning problem where we are trying to park this unicycle in some other orientation in some other location in the workspace, and the system is fully controllable, which means I can actually go and park it anywhere I want. Now, the mathematics involved in this is basically what we call the Controllability algebra, and what the Controllability algebra tells us is that if I want to go from this position here to here, I'm making this set of maneuvers. In the case of the unicycle, we were going straight, which can be taken as a vector field. Okay, vector field x. Okay, then I'm going to turn. This is another vector field. Okay, then I'm going to go back, which is minus x. That is another vector field, and then I'm going to go by minus y. So by making these 4 maneuvers, 1, 2, 3, and 4, I was able to go from here. If this is my unicycle, I was able to go from here to there, which is effectively going sideways. Now, what the Lie bracket tells us is that if you take the Lie bracket of x and y, when x and y are 2 vector fields, one is for going straight and the other is, we are going to generate a third vector field. Okay, so taking the Lie bracket of x and y, we are generating a third vector field, and this vector field is telling us that you can actually go sideways like that. Okay, not in one shot, but by making different maneuvers. Now, in order to do that, and where did that come from? That is basically when we are at a location, say q, and you are going to q dashed by del t squared, you're taking the Taylor series expansion and only retaining this term, okay, where dy into dx minus dx into y. Okay, and this is one vector field, this is another vector field. Now, dx is equal to this and dy is equal to that. So if I perform this operation, what I would get is a third vector field. Okay, and that vector field will actually be able to show me if there is any other direction which it can go. So in the case of the unicycle, something I discussed in the last class, I'll go through this very quickly here. So this is a wheel. Okay, this is my single wheel. It is making a contact, q1, q2, or x, y we can say, and it has an angle theta, which is q3. Okay. So the unicycle has 3, q1, q2, and q3, x and y and theta. Okay. Now, if I have 2 vector fields, the first vector field is the unicycle going straight, which is g1, so which is equal to cos x3 and sin x3 0. This is just going straight or going forward with unit velocity. This is one vector field. The other vector field, so this is one vector field. The other vector field is spinning or steering with unit velocity. So that is 0, 0, and 1. This is the second vector field. So we have 2 vector fields, g1 and g2. So if I take the Lie bracket of this 2 vector fields, what we get is a third vector field, g3, which is coming as sin x3 minus cos x3 and 0. Now if you look at it, it is sin x3 minus cos x3. So if you're looking at this in the top view, when you're looking at this, this is my x1, x2, x3. So minus cos x3 would mean that it is in the y direction, right? So if this is if you can imagine this to be x, that to be y, or this is x1, that is x2, then it is in this direction. That means it is in the negative direction of, so it is being able to come this side now. Okay, so this basically tells us that wherever the robot was or this wheel was, it can go in the other side of it, or it can go and park sideways. So it can go and park here now, like this. Okay, so this is mathematically telling us that taking the Lie bracket of g1 and g2, you are generating a third vector field, which is g3, and this is basically telling us that it can have a velocity in that direction, and that is what allows the wheel to actually go and park sideways. So this is also allowing the car to go and park sideways. Okay, now from the point of controllability, we say that the control algebra associated with delta, denoted by CLA, is the smallest distribution which contains delta and is closed under the Lie bracket operation. Okay, what is the meaning of closed under the Lie bracket operation? That means you can keep doing g1, g2, you get g3. Okay, now you can keep doing g3 and g1, you'll get something else. Now, is this closed or is it open? Okay, will you generate each time a new direction, or you'll end up getting directions which are not independent. Okay, that is the meaning of the word closed here. As we go along, we'll see this as we see our next example. Now, what is the point of this controllability business? The point of this controllability business is any two configurations Q initial to Q final of an open connected subset of C can be connected by a feasible path by following the flow of a finite sequence of vectors of delta if and only if the dimension of CLA is M, and M is also the dimension of the C space. Okay, so if I want to figure out if a system is fully controllable, I need to check this condition, that the dimension of the CLA is equal to the dimension of the C space. Okay, and if that is the case, then we can say that the system is fully controllable. And that also means that from an initial point, you can always find a path to the final point. That is the meaning of controllable, right? Now, as a corollary of this, we have that any robot that is subjected to a single non-singular scalar non-holonomic equality constraint is fully controllable. Now, if you remember, this is the car. The car is subjected to this constraint, and this is a single non-singular scalar non-holonomic equality constraint. Okay, and hence a car is fully controllable. Now, let's proceed further. Little bit more tricky, the tractor-trailer problem. Okay, in the case of a car, we understood that it is completely controllable and you can go and park it wherever you like. Now, what about the case of a tractor and a trailer problem? Okay, now suppose I want to figure out if this fellow from here can go and park there. Okay, then first the question I need to ask is this fully controllable? Okay, is this system fully controllable? Okay, if it is fully controllable, then only it can go and park like that, otherwise it can't. Okay, so how do we figure that out? We go back to our definition and see that if the dimension of the CLA is equal to the dimension of the C space, in that case the system is fully controllable, not otherwise. Okay, so let's look at this issue, look at this problem. Now this is basically showing us the tractor and the trailer. Okay, so please note that this is different. This is my tractor and this one is my trailer. Okay, you must have seen these tractor trailers in the roads carrying hay or carrying all kinds of goods. Now this is the setup of the problem. So first of all is that this is my x-axis, that's my y-axis. Okay, this is my tractor, it is shown here. The tractor has 4 wheels. The center point between the 2 wheels is Ri, and it has coordinates x1, y1. So Ri is the center point between the 2 rear wheels. R1, okay, and it is x1, y1 is the coordinate. Now the front wheels have a steering, which means that there is a phi there. So depending on the turn that you want to take or the turn that the tractor wants to take, we can change that phi angle and the tractor can take a turn. So when we are going straight, then that phi can be equal to 0. In that case, it is going straight. Okay. Now, how is the trailer attached? So the trailer is attached by a revolute joint here. So there is a revolute joint here, so it can rotate like this at that point R1, and it is fixed to the point R2. R2 has coordinates x2, y2. Okay, the where is R2? R2 is the midpoint between the 2 wheels of the trailer. Okay, so this is the setup of the tractor and the trailer. Now, a couple of things to note here. The first one is that the tractor is making an angle θ1 with the x-axis. Okay, that means I'm going to assign a local frame there. So this is my local frame, which is x, that's y. That's a local frame, right? Now that the tractor is making an angle θ1 with the x-axis. Now the trailer is making an angle θ2. Now because this is a revolute joint there, it can rotate like this or it can rotate like this. But there has to be some relation between θ1 and θ2, isn't it? Now the first thing to note here is that when this is taking a curve, say for example is taking a curve like this, the tractor is taking a curve like this. Okay, so the velocity at that point is going to be tangential to the curve. Okay, so let me draw it again. This is my curve that the tractor is taking. So the velocity at that point has to be tangential, so the velocity will be in this direction. Okay, what about the trailer? The trailer is taking a curve like this. Okay, and because of which the velocity would be tangential to the curve at the point R2. So both the velocities, this one and this one, are tangential at R1 and at R2. Okay, please note the directions in which the tractor is going and the direction in which the trailer is going. Now, okay, so and the other thing to note is that L2 is the distance between the point R2 and the point R1. So this is the R2. Okay, so now let's proceed and see. Now the tractor is subjected to a single non-holonomic constraint. Okay, similarly the trailer is also subjected to a single non-holonomic constraint. Okay, that means both of them cannot go sideways. This cannot go sideways, that also cannot go sideways. However, the trailer is related to the tractor, okay, because it is connected here with a revolute joint. Okay, now let's proceed and see how do we proceed to solve this problem. The first thing that we see is that how many degrees of freedom are there in the system. So the degrees of freedom are x1, y1, x1, y1, theta 1 for the this is for the tractor. This is the same as that of a car. Now there is a theta 2 there. This theta 1 here and a theta 2 there. This is for the trailer. Okay, so this one is for the tractor, that's for the trailer. Okay, now the non-holonomic constraint for the tractor, non-holonomic constraint for tractor is equal to minus x1 sine theta 1 plus y1 dot cos theta 1 is equal to 0. This is the same non-holonomic constraint that a car has because the velocity is tangential. This we had derived in the last class. Okay, so this is the tractor is behaving like a car. Okay, now what about the trailer? So this is for the tractor. What about the trailer? The trailer is also subject to a single non-holonomic constraint. Okay, now what is the non-holonomic constraint? It is minus x2 dot sine theta 2 plus y1 dot cos theta 2 is equal to 0. You see that it's almost similar to this. It's also a velocity constraint, and it is also saying that it cannot go sideways. Okay, sorry, it is not y1, it is y2. Okay, so both these constraints are saying the tractor cannot go sideways and the trailer also cannot go sideways. Now, is there some other relation between x2 and x1? And let's go back and look at the figure again. Now, this is my x1, okay, projection of, and this is my x2. So this is x2, y2, so projection is there. Okay, so which means that x2 is equal to x1 minus L2 cos theta 2. Okay, this is my cos theta 2. So x1 is equal to x2, which is this point. Where is x2? x2 is this point. x2 is equal to x1 minus L2 cos theta 2. There is one geometric constraint we have, and L2 cos and y2 is equal to y1 minus L2 sine theta 2. Okay, so we have these two conditions also. These two conditions are from the geometry. We have x2 is equal to x1 minus L2 cos theta 2 and y2 is equal to y1 minus L2 sine theta 2. Okay, from geometry. Okay. Now, if I differentiate and add to the first equation, that is equation 1, so this is my equation 1. Okay, then what we do get is combining these equations, we get x1 dot sine theta 2 plus y1 dot cos theta 2 minus L2 cos theta 2 dot is equal to 0. Okay, combining these equations, this is what we get. Okay, now what we see is that if I want to prove that if this system is fully controllable, I have to find 4 G1, G2, G3, G4, 4 motions, and show that the determinant of this 4 vector fields is not equal to 0, which basically means that all of them are independent vector fields. Okay, so what we are doing here is Like in the previous case, what we did in the previous case, if you remember, in the case of the unicycle, I wrote two vector fields. One was for going straight, which was cos and sine, and the other was 0, 0, 1. So here also I'm writing a vector field for going straight, which is x1. This is for going straight with unit velocity. This is equal to, this is one vector field, L2 cos theta 1. Second one is L2 sine theta 1. Third element is 0. Fourth is minus sine theta 1 minus theta 2. So this is one vector field for going straight. So going straight. Now another vector field for turning can be written as 0, 0, 1, 0. This vector field is only for turning because this is my angle theta, right? For the, this is my angle theta 1 for the tractor. Okay. Now if I use Lie brackets, then what we get is x3 is equal to x1 and x2 using Lie brackets, and this generates another vector field which is L2 sine theta 2, L2 cos theta 1, 0 minus cos theta 1 minus theta 2. Okay, so it generates another vector field like this. Okay, now this I have got x3 by taking the Lie brackets of x1 and x2. I can get another one x4 if I take the Lie brackets x1 and x3. Okay, so I take the Lie brackets x1 and x3, and what we get here is 0, 0, 0, minus 1. Okay, now if I find the determinant of all of these four, determinant of x1, x2, x3, and x4, okay, then we find that it is equal to L squared, which is not equal to 0, which means that these are independent vector fields. And because there are four independent vector fields, the degree of freedom of CLA, the dimension of CLA is equal to 4. And we have seen that if the dimension of CLA is equal to 4, and here also the degrees of freedom is 4, right? There is x1, y1, theta 1, theta 2, that's 4. So the dimension of CLA is equal to the dimension of C space, which is equal to 4, which means the system is fully controllable. Okay, so this tells us that this tractor trailer problem, this is very interesting because just by looking at it, it's very difficult to say. But once we do the analysis, we find that this system is fully controllable, which means that you can actually take the trailer, the tractor, and park it anywhere you want. Okay, and that is what is shown in this simulation also. Okay, even sideways parking is possible, provided it can perform a number of maneuvers. Now, this is a very interesting problem that you can have a tractor and a trailer, and this is a fully controllable system. It can go and park wherever you want. So it can go and park here, for example. Okay, it will be able to go and park here. Okay, so that is the interesting part of this problem, that we can prove the controllability of this system simply by using Lie algebra and proving that the dimension of the C space is equal to the dimension of the control Lie algebra. Okay, so we don't go further here, and we'll stop our discussion of controllability here, and we'll move on to the next topic, which is multi-fingered robot hands. Okay. Now, multi-fingered robot hands are normally used for dexterous manipulation. Okay. Now, in whatever we have studied in path planning so far, path planning objective is to prevent robots from colliding with objects. This is something we have seen, obstacle avoidance. And whatever we have done, like bug algorithm, probabilistic roadmap method, generalized Voronoi diagram, RRT, potential field, potential function, etc. The whole objective was obstacle avoidance. Okay, it was obstacle avoidance. Then here we made the assumption that it was a point robot and it could move in any direction. Then we talked about planning with kinematic constraints. In the case of mobile robots, cars, where there were non-holonomic constraints. Here the constraint is holonomic. Okay. This also has constraints, but they are holonomic constraints. Here it is non-holonomic constraints. Now let's look at a case where we are not saying we are going to avoid obstacles, but we are saying that the object has to be grasped by robot hands. That is, I have an object like this, okay, and it has to be grasped by 2 fingers in 2 directions, 2 or 3 fingers, let's say. It has to be grasped by a robot. Okay, that is basically called grasping of an object by robot hands. Now, this robot hands can be looked upon as manipulators. So this is something like a manipulator. Okay, and that's my robot hand. Okay. So it is like this is a serial manipulator, and this is making contact at this point. Now, in this particular application, grasping, you're seeing that the robot is actually making contact with the object, and it's constraining the object such that it doesn't move. That is the meaning of grasping an object. That is one. Okay, but after grasping an object, you may also want to move the object, just the way I showed in the beginning of the class, where I held the mouse, I grasped the mouse, and then I manipulated the mouse, I moved the mouse. That means I want to impart some motions to this object. Okay, so I also want to manipulate the object by multi-finger hands. So I need to perform some motions this side, or maybe this side, whatever. Okay, so we need to also look at grasping, and we need to look at manipulation. Now, grasping and manipulation are a little different from the, they are also path planning, because this object must move in a particular way, okay, and hence there has to be some path plan. Now, it's a little different in the sense of obstacle avoidance. We don't make contact. Here we are making contact, okay. So we also have to worry about the velocities and forces that are being applied, okay, because there is contact here. So the moment there is contact, it basically means that you can apply forces, moments, and there can be linear and angular velocities. Okay. So this is what we'll be looking at in multi-fingered manipulation. Grasping is one, and number 2 is manipulation. Now this is a very famous hand called the Salisbury hand. It has 9 degrees of freedom, 3 degrees of freedom per finger. And you can see that it has 3 degrees of freedom per finger. There is one here, that's 1 degree of freedom. There's the second degree of freedom, and there is 1 degree of freedom there. Similarly here, there is 1, there is 2, there is 3. Okay, so 3 degrees of freedom per finger, and there are 3 fingers. Okay, so it is 3 into 3, that is 9 degrees of freedom. This hand has. Now this hand can grasp. As you can see, it is grasping the nut there, but it can also manipulate. Okay, that means it should be able to rotate the nut or maybe move the nut in some way. How is it actuated? Basically, each joint is actuated by cables. So these cables run down across under the fingers and into the drives, which are located a little bit further away. These are all cables which are moving to the, so the motors are here, motors and pulleys, and when you tighten, when the motor rotates, the tension in the string changes, and that's how the fingers move. This is showing the internal construction of the finger motion. Okay, so there are cables. These cables are going through the pulleys and then are connected to particular joints. Okay, like this is connected here. This one is connected through the cable is connected here. So when this cable tension changes, what will happen? This joint will move. Okay, that is how the fingers of a multi-finger hand move. Another famous hand is the Barrett hand. So in the Barrett hand also there are 3 fingers. Now something I forgot to mention here is that there are 3 fingers. Okay, so this question may come to your mind: why 3 fingers? Why do humans have 5 fingers? We have 5. Okay, robots normally have 3, 2 or 3. Okay, whereas humans have 5. So how many fingers do you need actually? That's an interesting question. So the Barrett hand also has 3 fingers. It's a little different in construction, in the sense that it has a degree of freedom here, it has a degree of freedom here, and this full finger can rotate. Okay, so if I draw the side view of this, there is 1 finger here, 1 finger here, and 1 finger here, as shown here. So this is here, this fellow is here, and this one is there, as shown in this figure. But this can rotate this way, so there is a degree of freedom there, and it can change its position. So the fingers can rotate, and this finger can come here and come here. Okay, so depending on what kind of grasp you want, the finger base can rotate on the wrist, and you have 1 degree of freedom there. Okay, so each of the fingers also have 3 degrees of freedom. Now we are going to grasp an object and we are going to manipulate the object. Means we are going to have some kind of motion plan for the object now. I want to move the object in a particular way. Now, some of the questions that we need to answer. The first question is, how many fingers for grasping and how many fingers for manipulation? If you just want to grasp an object, okay, and then again the question whether you're talking of 2D or you're talking of 3D. Is it planar or is it in 3D? So how many fingers are required for grasping and how many fingers are required for manipulation? What should be the fingertip contact type? Okay, we saw that the fingertip contact has a particular shape. So this has a particular shape. The previous one had a different shape. This one fingertip has a spherical shape. The human fingers have a different shape again. Okay, so what should be the shape of the fingertip and what kind of contact? Because that is the one that will determine the contact type. Okay, forces, moments acting on the fingertip. Now, if you want to move an object, okay, you have to impart forces to move an object. Okay, so what are the forces, moments acting at the fingertip? What are the forces required for grasping? What are the forces required for manipulation? And lastly, how to impart desired velocity to the grasped object. Okay, so I have grasped an object and I want to move it along a path. Then how do I impart a desired velocity to the grasped object? Now here again, we need to look at the mathematics behind here. But unlike in the previous case where we talked about motion planning where the robot is not making contact with the object, here the robot is making contact with the object. Okay, so in terms of screw theory, we are going to analyze this, and here we deal with twists and wrenches. Okay, now twists are basically the linear and angular velocity along an axis. Okay, say for example, in this case, this finger is not making contact, so it can move. Okay, it can have linear velocities or it can have angular velocities about an axis simply because there is no contact with the object, so it's not constrained. Okay. Now, so these are called twists. So there are 3 linear velocities possible and 3 angular velocities possible. So 3 linear and 3 angular velocities possible. Okay, when there is no contact. Okay, so these are called the twists. Now, wrenches are the forces, moments which are possible to be applied to an object about an axis. In this particular case, okay, so here we talked about twists, here I'm talking about wrenches. So in case of wrenches, this finger can apply some force, it can apply some moment. Okay, so those are the forces, moments acting about an axis which the finger can apply to the object. Okay, so the motion of the object is going to determine on what? It will depend on the forces and motions being applied and what linear and angular moment velocities may be imparted to the object. Okay, and hence we use twists and wrenches for looking at the types of contacts, and then we try and decide how to impart a particular motion to the object. Now let's come to some definitions before we go into the mathematical analysis. So the definition: twist is a combination of translational and rotational velocity of an object. It can be defined as Vt and omega t. Okay, so how many Vx, Vy, Vz and omega x, omega y, omega z. So these are angular velocities about an axis and this is linear velocity along an axis. Okay, so there are 6 here. Okay, so these are called twists. Now of course, twists are possible if there is no contact. The moment the object makes contact, the moment the fingertip makes contact with the object, it will get constrained. It may get constrained. Now what is the wrench? Now a combination of the force and moment applied to the object by the fingertip is called a wrench. So a combination of force and moment applied to the object by the fingertip is called a moment. Now you may be able to apply some forces in some directions. You may not be able to apply some forces in some directions. It depends on the type of contact. Okay. Now what is the wrench space? So there are forces and there are moments. So there are 3 forces: Fx, Fy, Fz and Mx, My and Mz. Okay. Now what is the wrench space? The space of wrenches applied to the object. In 3D, there are 6-dimensional wrench space, 3 forces, 3 moments. In 2D, there are 2 forces and 1 moment. Okay, so we are seeing that in case of twists, there are 6 in 3D. In case of wrenches, also there are 6 in 3D. Okay, so one force and moment along every axis. Similarly here, 1 linear velocity and 1 angular velocity about every axis. So the wrench space and the twist space are 6 and 6 in 3D, and it is 3 and 3 in 2D. Okay. Now, how do we grasp an object? That's the first question. Okay, this Salisbury hand is grasping the nut. So there is some contact being made between the fingertip and the nut. There, one here, one here, and one here. Now, depending on the type of contact that is being made, there will be forces and moments that can be applied. What do I mean? For example, depending on the kind of contact. If no contact is there, then you cannot apply a force. You can apply, it can only have twists, right? So again, the kind of forces that can be applied would depend on, for example, mu, the coefficient of friction. If mu is equal to 0, okay, then you cannot apply forces which are orthogonal to the normal force there. Okay, so that contact conditions determines what are the twists and the wrenches acting at a contact point in a finger. So twists and wrenches for fingertip contact types. Okay. So if there is no contact, okay, so we have an object here and the finger is here. Let's say this is my finger. Okay, that's the finger. Okay, and there is no contact. So in that case, how many twists and how many wrenches are possible? And wrenches, now if there is no contact, you cannot apply force. So there is no wrench possible, so it is 0. So null wrench means 0 wrench. Okay, you cannot apply any force at any moment because there is no contact between the finger and the object. Okay. Now what about twists at the fingertip? You can apply 3 linear velocities and 3 angular velocities. So there is 6 here now. Okay. So when there is no contact, you can apply 6 twists but 0 forces, 0 wrenches. Now, so no contact when the object and the finger are not making contact. The moment you make point contact with friction, now let's look at this example here. This is point contact with friction. So this is an object, and let's say this is point contact here with friction. So mu is there. Okay. Let us write our, this is one axis, x-axis, y-axis, and that's my z-axis, x, y, z. Okay. So now the moment there is this is without friction, right? So there is no friction. Now, if there is no friction means you can apply a normal force along the z direction. So you can apply a force this direction, okay? But you can't apply a force in that direction, that direction. Why? Because mu is equal to 0. There's no friction, okay? So this is my normal force in this in the z direction. Please note it's in the z direction. But there is no force in the other directions, okay? What about moment? Now you cannot apply a moment also because it's a point contact and there is no friction. So mu is equal to 0. So it won't support a moment. Okay. So in that case, what are the twists possible and wrenches possible? Let's look at the wrenches first. So in that case, we can apply a wrench. This is my Fz. Okay, so this is my Fx, Fy, Fz, Mx, My, Mz. Okay, these are three. So in this particular case, only Fz is possible. The others are all 0. That is the meaning of writing it like this: 0, 0, 1, 0, 0, 0. Okay. What twists are possible? Okay. Now the twists that are possible are shown here. The first is that one twist will not be possible. Okay. Which twist will not be possible? Because there is the fingertip has made contact here like this. Contact has been made. It cannot go in this direction, right? It's constrained now. So it is constrained to move in this direction, in the z direction. That means if you see here that T6, which was there here, the last one, that is not there. That's a linear velocity. So it is omega x, omega y, omega z. Then in terms of the linear velocities, it is Vx, Vy, Vz. So in this particular case, that Vz fellow, okay, is the one that you cannot have. You cannot have a velocity in that z direction because it is constrained. The object is there. The finger cannot go through the object. Okay. So there are only T1, T2, T3, T4, T5, and T6 is equal to 0. We don't write it. Now there is a relation between the T6 and this omega 1. You can see the velocity which is not possible is in the z direction. And the force that you're applying is also in the z direction. Please note that. So this is my z direction. That's my z direction. So I'm applying a force in the z direction. and the velocity is getting constrained in this direction only. That means if the system is constrained there, if the finger is constrained to the object there, only then you can apply a force, not otherwise. Okay, and there is correlation that the total of the wrench and the twist must be equal to 6. So total of wrench plus twist must be equal to 6. Okay, so if you have one wrench here, there will be 5 twists. That means one twist is gone. So this is point contact without friction. The next is point contact with friction. Now as you can see that this is my x, y and z. Now there is friction there, so mu is there. Let's say there is a constant value. Okay. Now because mu is there, we can apply 3 forces. One force here, normal force. And because of mu, there's going to be a mu into n there, which is in this direction and this direction. So F by n is equal to mu. Okay. So there is going to be a force in this direction and this direction, which is proportional to the normal force into the friction coefficient. Okay, so I have 3 forces which are possible. So you can see that W1, W2, W3, this is Fx, Fy and Fz are possible. What about twists? In case of twists, because you can apply forces, you cannot have a linear velocity. Okay, it won't allow you to move in that direction. But the angular velocities are there. So omega x, omega y, omega z are there. The Vx, Vy and Vz all become equal to 0. Okay, so we have 3 here and 3 here, totally 6 again. Okay. Now, please note that this is point contact with friction, and most robot fingertips are this type, point contact with friction. Okay. Now, in order to have a little bit better grasp, sometimes the robot fingertips are coated with a rubber pad or they are slightly soft. Okay. And also the human fingertips, if you see, we have the bone inside the fingertip, so we have the bones inside the fingers, and there is tissue on top. Okay, so this is my nail. Okay, then there is tissue on top. Okay, so this is soft. The tissues are soft, and they also have friction. So they are soft plus mu. So this is called soft finger contact. And in soft finger contact, please have a look at this figure here and try to understand this very clearly. So this is my x-axis, y-axis and z-axis. Now in the soft finger contact, let's look at the forces. Because there is mu, mu is there. So 3 forces we can apply. Okay, like in the previous case. Here also we are applying 3 forces. So W1, W2, W3 is there because we can apply forces there. And there is mu. And we have one additional moment which we can apply, that is my W1, it is the W3, this one. So which is it is written as W4. This is in the Z direction, WZ. Okay, so I have 3 forces, Fx, Fy, Fz, and a moment. And moment which is my, well, let me call it M. I've been using M, so M, Z. Okay, so I can apply 3 forces and 1 moment. Which moment? Moment about this. Why? And if I draw the top view of this again, what you can imagine is, if I draw the cross section of the finger is like this. So it can resist a moment about that. There's a surface contact now. Okay, so the finger is making contact with the surface. This is my surface. So the finger has deformed. That's my deformation. So the finger can resist a moment in that direction. Okay, because there is friction and there is surface contact now. So it can resist a moment. It can resist moment, but it cannot apply moment. So it's a passive contact there. Now, because of this, there are 4 here. Now, if there are 4 here, then there are only 2 left here. So which 2 are left? So you cannot have a velocity in the, there are only 2 of this left. So if there are 2 left, which 2 are left? So omega x and omega y are left. Okay, so moment about this and moment about that. That is the only one left. And motion is constrained. Linear velocities are constrained in the x direction, y direction, z direction. They are constrained. It can't move. And there is one moment in this direction. Okay, so it will not allow you to rotate about z. So it will only allow you to rotate about x and about y, and that is this one. So wx and wy. So it is allowing rotation about x and y axis only, but not about z axis. Okay, and again this is 2, so it is 4 plus 2, which is equal to 6. So before we are analyzing any multi-finger manipulation, now let me make a point here. If you are wondering what is the relation with motion planning or path planning, in this particular case of application, I want to impart a particular motion to this nut. For example, I want to tighten this nut, so I have to rotate it about an axis. To rotate this nut about an axis, I have to impart forces and moments. And rotation means I have to impart some desired velocity. Okay, so that is what this analysis is going to tell us, that what is the relationship between the fingertip forces moments and the resultant velocity of the object. That is one. Think of it this way. I have two manipulators. They are holding an object. Okay, so this is one manipulator. It's holding an object here, and there is another manipulator here. This manipulator is fixed. It's something like the hand. Now I want to impart some motion to this object. That means I want to give it some velocity and I want to move it in some direction. In that case, I have to impart forces here, right? So I need to figure out what are the forces to be applied in the fingertip such that the object has a resultant motion, right? Look at it. So this is for the case of a serial arm. Look at the case of mobile robots. We have multiple mobile robots which are catching, this is what is called swarm. So we have multiple mobile robots which are catching this object. Let me have this object. These are small robots which are catching this object and pushing it and taking it somewhere. Okay, so these are small robots which are, this is an object. It is capturing this object and pushing it somewhere. This is we can call swarm robotics, we can call multi-agent system. Okay. All of them use the same logic. Okay, so this is in a way a multi-agent system also. So depending on how the contact condition is there between the robot and the object, you can apply forces, that means wrenches or twists, right? So whenever a robot is making contact with, whenever two surfaces are making contact, okay, in our case the robot is making contact with the object. For example, I have this object and there's a circular robot which is trying to push it and take it somewhere. Okay. So what is the contact condition would be depending on any of this. It could be point contact, it could be point contact with friction. Now if it is point contact with friction, then it can apply three forces there. Okay. Now if it is point contact without friction, it can apply one force only, that's the normal force. Okay, so this is what determines how many forces and moments can be applied, and that depends on the contact condition. Okay, so the final resultant motion of the object would depend on the forces moments being applied by the multiple robots which are pushing it or capturing or doing whatever. So it can be robotic fingers, it can be serial arms, it can be mobile robots, multiple swarms, it can be UAVs catching an object and pushing it somewhere. Okay, in all cases it is the contact conditions that determines. Now first let's look at grasping. Okay, now this is an object which is being grasped, or an object here which is shown in the figure. This is an object and it is three contacts which are there, one contact here, one contact here, and one contact here. Okay, now you can assume this to be something like a box which is caught with three fingers like this, the same thing. Okay, or let's look at an object with multiple mobile robots. One robot is here, one robot is there, one robot is there. Okay, so this is a multi-agent swarm. They all mean the same thing. Then this is just simple object grasping. The theory and the maths is the same. Okay. Now in this particular case of grasping basically means you want to hold an object and ensure that object is stable under external disturbances. Okay, so what is grasp? Is to hold an object and see if it's stable under external disturbances. Okay. Now here we use two terms. One is called force closure and the other is called form closure. Now when you're catching an object by using multiple hands or multiple robots or multiple swarms, okay, we need to analyze and understand something, that the forces are unisense forces. Forces can be applied only in one direction. Okay, so this is something please keep in mind. So when you're looking at this contact condition here, okay, the force can be applied only in this direction. Okay. There cannot be a force in this direction. It's not possible. It's like pulling the object, right? I hope you understand that. So if you have an object here and you're pushing it from here, you can't pull it like that. Why? Because the contact will break immediately. So these forces are in one direction only, and this is what we call unisense direction of forces. They are not bidirectional. So these are unidirectional forces. Now in force closure, like here, even if the rank of the matrix of screw coordinates is 6, okay, only a subset of disturbances acting on the body can be resisted by the grasp. That means if you catch an object like this, okay, and you're under force closure, that means I can apply forces like this, and the rank of the matrix of screw coordinates is 6. Okay, why 6? Because at most they can be 6, right? Degrees of freedom are only 6. 6 forces, 6 moments. So if the rank of the screw coordinate matrix is 6, even then only a subset of disturbances can be acting on the body can be resisted by the grasp. This means that in this left side figure here, this grasp in a way is not stable. It is stable only with a limited number of forces or disturbances. Stable for only a limited number of disturbances, number of external disturbance forces. Okay. Now what this means is that it has caught, okay, suppose you can argue that this is gravity. So this is having a force here, this is having a force in this direction, this is having a force in this direction, and it is stable. But the moment I use a force in this direction, if I push it in this direction, it will immediately come off. Okay. Why? Because it cannot resist forces in this direction. There is no contact which is going to resist forces in that direction. So this contact cannot resist force in this direction. This fellow cannot, and this fellow cannot, because they are unisense direction of forces. Okay. So this is something to note, that when you are catching an object, like here, in this particular case I was showing, are you under force closure or are you under form closure? In force closure, you can apply, you are subjecting the system only to unidirectional forces, and that cannot resist all forces that can come on the object. It can resist only a subset of forces. Okay. It can resist only a subset of disturbances that can come on the body. So this is the catchword, subset of forces, of disturbance forces. In such cases, it is under force closure. And for example, this is the example he also gave. So this was invented first by Reuleaux in 1963, this is a very long time ago. If you take a cube, okay, this is a cube, and we are holding it by 3 line contacts. So a cube constrained by 3 line contacts with friction. So one line is like this, one line is like this, and one line is like this. I can also give the idea that if this is a cube, let's say this is a cube, I'm sure you must have felt this or seen this or experienced this somewhere. If you place one finger here, one finger here, and one finger here, this is equivalent to saying you're holding it here, here, and here. You can still hold the cube, right? If this is a finger like this, another finger here, another finger here, these are 3 fingers, and you're holding it like that. Okay, you can still lift the cube, right? You can lift. Okay, that means you can grasp the cube, hold the cube, just by holding it like that, using your 3 fingers. You can do that. Okay, but you are under force closure. Why? Because all disturbances cannot be rejected, which means that there will be disturbances which is going to destabilize the system. That destabilize here means basically the grasp will fail. So what I mean basically here is grasp fail. Okay, that's what I mean by stability here. So in this particular case, this is under force closure. So I will be able to hold it and probably lift it by holding on these three sides, either by line contact or by soft finger contact. But the moment there is a force in this direction, there's a force in this direction now, pushing it in that direction. Okay. So the moment there is a force which is pushing it, if you can imagine from this point it is pushing. Okay. So let me draw it like this. This is a force F. It will immediately go that side. Okay. Similarly here, if I now apply a force from here like this, what will happen? The cube will come off this side, because these fellows are unidirectional. Okay, they can only resist forces in this direction, but they cannot resist forces in that direction because they are unidirectional forces. Because of which this term was coined called force closure, which means that although you are grasping an object, but it is not a stable grasp, it can get destabilized very easily. Okay, if the force comes in another direction, it will destabilize. Okay. Now, so that is one force closure. The other is what we call form closure. Now, if collection of wrenches, bidirectional, unidirectional, acting on an object can resist arbitrary disturbances. Now, if you can resist arbitrary disturbances, that means you can resist, arbitrary means all disturbances, then we say the system is under form closure. And for form closure, this was invented by Lakshminarayan in India itself, 1978. And he proved that 7-point contacts without friction are required to form closure of 3D object. So if I have a 3D object like this, this is a cube. So I'll be requiring 7-point contacts. Okay, one here, one here, one here, one here, one that side. So there are 6 faces, right? So there are 6. Plus you'll need 1. This 1 because some of the forces are all unidirectional. Okay, so the 6 plus 1 equal to 7. And here's the first one who proved that 7-point contact without friction are required to have form closure of 3D object. And 4-point contact without friction are required to form closure of a 2D planar object. So if I have a 2D object like this, I need 4, okay, to have form closure. That means I can put 2 here, and I can put 2 here. Now this is completely constrained. It will not get destabilized anyway, due to any disturbance also. So it can reject any arbitrary disturbance. And this is what we call form closure. Okay. So today we looked at multi-finger manipulation, and in the next class we'll be moving on to looking at how do you apply the forces in order to move an object in a particular direction. Okay. Then we'll look at multi-agent system where there are multiple robots which are trying to push an object in some direction and imparting some motion. Okay. Now this is applicable also to multi-agent systems, to unmanned aerial vehicles which are trying to push an object somewhere. Okay. So we'll stop here today. Thank you.